Hello girls, in this lesson we're going to be looking at the binomial distribution, which is one of two discrete probability distributions that we'll be looking at. So just as a matter of recall, you might remember that a discrete probability distribution is a distribution in which the random variable can only take on exact values. So it's like tossing a coin, and it can either be heads or tails, or tossing a dice. We can either get a 1, 2, 3, 4, 5, and 6. We can't get 1.5, or we can't throw something else on a coin other than heads or tails. All right, so that's what a discrete probability distribution is, exact values. So let's look at the binomial distribution. You already know that the word binomial means two. So the idea in a binomial distribution is that it's a discrete distribution that has events which only have two mutually exclusive outcomes. All right, so the one outcome is a success, that's what it's known as, and the other outcome is a failure. What that means is if I talk about the probability of throwing a heads when we toss a coin, if the coin lands on a head, that's a success. If it lands on a tail, that's a failure. All right. However, if I rephrase the question and said, let's look at the probability of a coin landing on a tail, then the tail would become the success and the heads would become the failure. Okay, so some other examples of binomial distributive events that are discrete are, as we've said, tossing a coin, soccer game finals, say finals particularly because it can't be a draw. Someone either has to win or someone has to lose. So there are our two different ways of getting a result. Test answers, either it's correct or it's incorrect. Let's think about multiple choice tests. A driver's test, you either pass or you fail. There's no middle ground. And like we said, rolling a dice. But with rolling a dice, there's 6 options. So it's not just rolling a dice on its own that's binomially distributed, but it's an outcome of either getting an even or an odd number. Let's now look at the properties of the binomial distribution. Right, so firstly, there are only 2 possible outcomes on each trial, hence the name binomial. We discussed this previously. Secondly, the outcomes are mutually exclusive. So in other words, if you had to draw a Venn diagram, there would be no intersection of the 2 events, the 2 circles, and there would only be 2 circles. And thirdly, each trial is independent of any other trial. In other words, if I throw the coin and it lands on heads or tails and I record that, that has no impact or influence on the next time that I throw that same coin. And lastly, the probability of success or failure remains unchanged at any trial. So, in other words, it doesn't matter how many times we throw the coin, the probability of it landing on heads, if that's our success, or tails, if that's our failure, will not change. All right, so just a little bit more on this example of heads or tails. I'm sure you can see that they follow all 4 of those properties in that, firstly, there's only 2 possible outcomes. The outcomes are mutually exclusive. We can't have half heads, half tails. Each trial is independent of any other trial because it doesn't matter how many times we toss the coin, the outcome will not be affected of any given coin toss. And then lastly, as we've discussed, the probabilities will remain the same every time we toss the coin as to what is expected to happen. So effectively, the binomial distribution is an extension of a replacement-based tree diagram, okay, where we have an event, a trial at least, and we maybe throw the coin or throw the dice or whatever, and then we have another trial and we do that again. But with a tree diagram, you only kind of go up to maximum 3 times, whereas with the methods that I'm going to show you now, we can look at this extending to 15 times maybe. All right, which would be really, really messy if we had to draw a tree diagram for 15 different trials. Right, so let's look at example 1 together. Example 1, you can follow this on page 122 of your green stats and probability textbook. You don't need to write out the example. Tandi is a good goal shooter in netball. The probability that she scores on any given attempt is 70%. She's practicing and takes some shots at the net. To begin, let's assume that she takes 3 shots at the net. So in other words, we could easily do this with a tree diagram. What is the probability that she scores exactly A 3 times, B 2 times, C 1 time, and D 0 times? First thing we're going to do is we check if this follows a binomial distribution, because we're going to apply a certain method or algorithm to this. Okay, so firstly, and if you go back to your properties on the previous page, firstly, there are only 2 outcomes. She can either score or miss. Secondly, scoring and missing are mutually exclusive. She can't miss and score at the same time. And thirdly, she takes 3 shots, and each shot is independent of any of her previous shots. And lastly, her probability of scoring is 70% on any given trial. It didn't say that 70% the first time, and then maybe she's affected psychologically, so if she scores, if she doesn't score on the first time and she's only got a 50, that would make it not binomial distribution. We're assuming here that her psychology is not affecting her at all, and each shot she takes, she has a 70% chance of scoring. Right, so let's make some notes as to what we do know. We know that the number of trials is 3 shots. She's going to take 3 shots in a row, and that means that n is equal to 3. The random variable is the number of shots that Tundi scores. So if we say let x equal the number of shots that Tundi scores, so we'll actually write that out. Let capital X equal the number of shots scored. We can represent that, as you know, in a set. Okay, she can either score no shots, she can score 1, she can score 2, or she can score a maximum of 3 shots. It also makes sense that because we're looking at her probability of scoring, and the question says what is the probability that she scores, not that she doesn't score. So the fact that she scores will be our success, and the fact that she misses will be our failure. Quite harsh, actually, when I think about it. All right, but we're not saying that she's a failure because she missed her shots. Well, she was at that particular shot, but she's not a failure in life. So the probabilities of her either success or failure, we use a lowercase p to denote the probability of success. So that's given as 70%, or 0.7. And in the failure outcome, or the miss, we use q. So her probability of q then is obviously 30%. Remember, they're mutually exclusive. So if there's 70% of scoring, chance of scoring, then there's only 30% chance of not scoring. Right, it also follows that these 2 outcomes are complementary. All right, they're one or the other. So it means that our probabilities can be shown as p plus q, which is equal to 1, which also means that q is equal to 1 minus p. All right, so something that we'll look at a little bit later. So let's just summarize what we have. We've got the trials. The number of trials is 3. Her probability of success. Listen, I'm using the language of binomial distribution, not just of this particular example. Okay, so instead of saying her probability of scoring, I'm now saying her probability of success, okay, is p is equal to 0.7. Her probability of failure will be q is equal to 0.3, and we've already defined her random variable as 0, 1, 2, and 3. 4 possible outcomes for all 3 trials, okay, in total. So the tree diagram for this scenario would look as follows. So you can see on the first trial, she has a 70% of scoring or a 30% of missing. Then after she's taken the first trial, there's again a 70 or a 30, and so on, a 70 or 30. So we have our 8 possible outcomes here that she can have. Okay, either if she's really having a good day, she'll score 3 times in a row. If she's really having a bad day and is about to be dropped from the team, then she'll have 3 misses in a row. Okay, and then everything else is in between. So let's look back at the question. What is the probability that she scores exactly 3 times? We're going to look at A first. Right, so you can see we have highlighted in green, in pink there, that would be the path if she was going to score 3 times. That's the only possible path. All right, so we could answer this as follows. You could say that the probability that she scores 3 times is equal to 0,7 times 0,7 times 0,7. Right, and we don't have to worry about the answer for now. At the moment, we're just looking at how we can structure it out. Another way that we can do it is as follows. Okay, the probability that she scores 3 times is equal to 1 times 0,7 to the power of 3 times 0,3 to the power of 0. All right, now what this all means is the 1 represents one way, because there's only one way that she can score 3 times in a row. If we were looking at what are the possibility or the probabilities that she only scores 2, as we'll look in another one, then that changes. All right, and then that represents the 0,7 to the 3 represents all 3 shots scored, and the 0,3 to the 0 represents none missed. Okay, so that's just another way to represent the same information. All right, question B, what is the probability that she scores exactly 2 times? Now, as we're going along, I want you to see if there's a pattern that's arising, because we first asked for 3 times, now 2 times, and then C goes 1 time, and D goes 0 times. So we're going in order from the most possible scores to the least possible scores. All right, but let's have a look at B. Right, in order to score twice, and we're implying exactly twice, so we can't argue that if she scores 3 times that she has scored twice, plus 1 extra. No, she scored 3 times then. We're looking at exactly 2 scores, and the order doesn't matter. So let's look at the different pathways. The first pathway is this one to SSM. The second pathway is to this one to SMS. The third pathway is to MSS, and there are no more pathways after that. So there are only 3 different possible outcomes. All right, so we can start off by showing which random variable we're working with. Well, it's still x equals, but now 2 shots. All right, and remember I said we were looking at how many ways? There were 3 ways now. Okay, those 3 ways are represented in the table by those 3 that I've highlighted in yellow there. All right, so there are 3 ways times now 0,7 to the power of 2, because we're looking at her scoring 2 shots for each of those 3 branches on the tree diagram. All right, and then there will obviously, for 2 shots scored, there will be 1 shot. Sorry, that should be 0,3 to the power of 1 shot that is missed. Right, let's look at C. Now, before I move on, I'm going to add in A's answer just at the top there, now that we've got space. And now let's quickly look at question C. Question C, what are the probabilities that she scores exactly 1 time? Right, so for question C, we can again let's look at the diagram to see how many times she scores exactly once. The first option where she scores exactly once is on this pathway, okay, SMM. The second option where she scores exactly once is on this pathway, MSM. And then the last option is she scores MMS on that pathway. So again, there are 3 different ways to score 1 shot only. All right, so if we go into our notation now, we're looking at 1 shot. So we've already seen there are 3 ways of scoring 1 shot, because 70% is her score rate. And that is multiplied by 0,3 to the 2 for each of the other shots in that particular group of 3 that she didn't make. Okay, let's look at D. What is the probability that she scores exactly 0 times? So obviously the only possible pathway is this MMM at the bottom. Right, so let's write that in proper notation. So the probability that she scores 0 times, there's only one way to do that now. 0,7 would be raised to a 0, and 0,3 would be raised to a 3 because she has missed all 3 of the shots. Okay, at this point, I'm also going to put the answers in for all of these just because, you can see then what your final answer would be. But as I said, we're actually on our way to investigate something. So the answer at the moment is not the most important thing, but it's useful to see what it is. So 0,189 for scoring exactly 1 shot, and the probability of scoring no shots is 0,027. Okay, so I want you to start looking at what pattern we have. All right, so we have, in terms of the number of ways, 1, 3, 3, 1. Our exponents for the probability of successes is going down, 3, 2, 1, 0. And our exponents for the probability of failures are increasing, 0, 1, 2, 3. Okay, these always add up to 3 because there are only 3 trials. All right, and they're complementary events, they're mutually exclusive, so those exponents are always going to add up to 3. All right, one extra thing I want you to write down here is the following. The probability of X occurring is the number of ways times the probability of success times the probability of failure. Okay, that's kind of a general description of what's happening above, but we're going to come back to that. All right, so in front of you, you see the first 4 rows, of Pascal's triangle. And so the number of ways part, as you saw in the previous slide, where we had the 1, 3, 3, 1 on the left-hand side here, actually corresponds to what is known, it forms what is known as binomial coefficients, and this has to do with combinations, which were studied in chapter 3, so we did that a bit last year, and is easily understood by Pascal's triangle. Okay, so if you want to follow these notes in your textbook, I'm on page 125. Okay, so for each of these at the bottom, we now have 3 choose 0. In other words, scoring 0 out of the 3. There was one way to do that. That was the last one. Or we have 3 choose 1, which meant scoring 1 out of the 3 different ways. There were 3 ways to do that. Okay, hence the 3 in pink. And then we have 3 choose 2, and that means scoring 2 out of the 3. Remember, there were 3 ways to do that as well, where you had an S, an S, and an M in whatever order. And then lastly, we have 3 choose 3, which meant scoring 3 out of all 3. Okay, now you can just use the NCR function on your calculators to work these out. We're going to get closer to that shortly. But Pascal's triangle is a nice way to see where this binomial coefficient comes from. All right, so let's look at rewriting our answers now in combination form. Right, firstly, we're going to look at probability of X equaling 0. So we're going to now look at 3 choose 0. All right, and that meant that there were no scores, but there were 3 misses, so to the power of 3. Okay, and that was 0,027. And again, remember the exponents over here must add up to 3. Right, then the probability of scoring once is now 3 choose 1. That means 0,7 to the power of 1, multiply, times 0,3 to the power of 2 now, because there are 2 misses. Okay, let me do one more with you. So the probability of scoring twice would now be 3 choose 2 times 0.7 to the 2 times 0.3 to the 1 now, which is 0.441. Right, so I've just put the last one in there, the probability of scoring all 3 shots. All right, now let's put this in as a variable now. All right, we can say that the probability of x occurring x times will be equal to 3 choose x times 0.7 to the power of x times 0.3 to the power of 3 minus x. Right, one other thing I want you to check is if we sum up all the probabilities on your calculator, you will get 1, or very close to 1, because we've probably rounded off a little bit, but you'll get very, very close to 1. All right, but now let's look at the flaw so far. This model only works for if there were 3 shots. So remember, it doesn't have to just be netball. It could have been anything. We could have been looking at a coin toss, etc. But it only looks at success a maximum of 3 times, because there's a maximum of 3 tosses. All right. So let's look what we want. Let's look how we could devise some formula where we are not limited to simply 3 trials. And that's why we would not always use a tree diagram. A tree diagram is helpful when there are only 3 trials, but try and do a tree diagram with 15 trials of shooting netball goals, and you'll see that it just becomes ridiculous. Right, so the formula in front is how we summarized it if there were 3 shots that were taken. But now we're going to say, let's assume that instead of 3 shots, Tandi is now taking n shots. All right, so the formula is going to look exactly the same, in that we're going to just replace the 3's with n's now. So it's going to become P capital X equals little x is now equal to n choose x times 0.7 to the x times 0.3 to the n minus x. Now remember as well from a previous slide that P was equal to 0.7 because that was the success. So I'm going to actually just remind you that P represented success and Q represented the failure. So now we can go one step further and show this in terms of P and Q. Right, so the probability that an event occurs x times is now equal to n choose x, right, times, now instead of 0.7, we're going to use P to the x, and then 1 minus P to the n minus x. Okay, why we're using 1 minus P is, remember, we worked out Q by subtracting P from 1. Okay, because P and Q aren't independent of one another. They're very definitely linked to each other. All right, so there you have the binomial distribution formula, all right, where n is the number of trials, where P is the probability of success, and remember that's on each trial, and 1 minus P, which remember is the same as Q, is the probability of failure. And lastly, x, little x, is the values of the random variable. All right, so in this case, those were they can go up to however many. There's no restriction on those. Okay, so in this case, it went up to 3 because she could get a maximum of, well, it went up to 3, but we started at 0, so there were 4 different outcomes that she could either miss all of them, or get only 1 of them, or 2 of them, or all 3. Right, to end off this lesson, let's have a look how we can apply this now. Let's say that Tundi, instead of just taking the 3 shots, decides she wants to take 6 shots in a row. Now, a tree diagram like this would be way too cumbersome because the tree diagram gets exponentially bigger each trial that you look at. So now we know that n now equals 6, right? Because there's now 6 possibilities, all right, of what's going to happen, because she's got 6 different trials. And p is still 0,7. That hasn't changed. The random variable now becomes 0, 1, 2, 3, 4, 5, 6. Right, that's now the random variable because there's now up to 6 possibilities for her 6 shots. All right, she can get all 6, she can miss 5 and get 1, she could miss, and so on. All right, so without drawing a tree diagram now, we would be able to immediately link this. Okay, so before I carry on with this, I wanted you to just look quickly at the Pascal's triangle. Right, in Pascal's triangle, this is known as row 0, this is row 1, this is row 2, and this is row 3. So because there were 3 shots, we use that row to make up our 3 choose 0, 3 choose 1, etc. Right, so I'm going to show you the Pascal triangle in a minute, but for now, let's have a look at what our options are here. So let's look if she looks at x equals 0, in other words, the probability of missing all of them and not making any shots, that would be 6 choose 0 times 0,7 to the 0 now times 0,3 to the 6, okay, which gives us a probability of 0,00072. All right, then let's look at probability of x equals 1. So the probability that she makes 1 out of the 6 shots is now going to be 6 choose 1 times 0,71 shot only times 0,3 to the 5 now, because remember those exponents must always add up to 6. Okay, and then that gives us 0,0102. Right, let me do one more. The probability that she makes 2 of the shots will be 6 choose 2 times 0,7 to the power of 2 times 0,3 to the power of 4. That gives us a probability of 0,0595. All right, I'm not going to go on because you can see the pattern now. If you want to see the rest of this exercise, then have a look on page 126 right at the bottom. And also shows you on page 126 of your green book that if you used Pascal's triangle for the combinations, you would have used the 6th row. And the 6th row gives us 1, 6, 15, 20, and so on. And these values here, 6 choose 0 gives us 1, 6 choose 1 gives us 6, 6 choose 2 gives us 15, and so on. Right, we're getting close to the end of this lesson, but what you see in front of you here is a graph, as you remember from your revision, random variable graphing, for when she took 3 shots and for when she took X shots. So if you need to pause the video now to have a look and understand that graph that represents all the probabilities, you can do so now. Okay, so what we can see for both of these graphs is that it's skewed more to the right than to the left, not in the middle. So, for example, if we look at the halfway line here, she's definitely more in this side of the graph. And if we look at the halfway line between 0 and 6, which is right here by 3, then she's also, again, there's more chance that she will score than more shots than less shots. All right? In other words, data is more popular to the right-hand side. And it says she's a good netball player, she scores 70% of the time, etc. So if you had to think, what would make this more equal? In other words, more of a bell curve, okay, where instead of having it more popular to the right there, you would have something that looked more like that, or for the second one, more like that. What would have to happen? Okay, so let's play around with different values for N, 6 shots, and in the last one, 50 shots, but different values of P. So if you look at the first diagram, so we're looking still at 6 shots, but now her probability of success is only 0.25. Okay, and there you can see that it's now populated more to the left. Right, then N is equal to 6, that's the middle diagram, but now her probability of scoring or success is 50%, which means that her failure rate is also 50%, and there you get a perfect bell curve. Okay, and then if we expand that to the same value as P, but with 0.5 as P, but with 50 as N, in other words, she takes 50 shots in total, we still see a bell curve. The pieces are getting closer and closer together, but it's even. It is not populated either to the left or to the right. Right, that's the end of today's lesson. So I'm giving you tomorrow, well, Monday, it's Sunday for me, I'm giving you Monday and Tuesday to complete this lesson. There's no work to do with this lesson, but if you do have time, I would suggest you go through the textbook notes as well. This starts on page 120, up to 127. Those are the pages that we've covered in this lesson.